We're going to go through an example exercise in Python programming on how to compute an adiabatic flame temperature. So the homework is right here on the right of the course website at APMonitor.com/CHE263. If you come down to homework and then just scroll down, we're on assignment number 14. And so you can look at the solutions to problems 1 and 2. Those are just simple one variable, two variable problems. We're going to jump down to this problem number 3, which is an adiabatic flame temperature for methane air flame. So if you need a little bit of help on the adiabatic flame temperature, you can come to another video that I did on adiabatic flame temperature in Excel. It explains a little bit more about adiabatic flame temperatures. Okay, so if you haven't done so already, come to the you just go back to that homework link on the right, and then the files are going to be here available for download under the files link. And then once you finish downloading that, then you can unzip them, and we're going to work through the problem that's here in the IPython notebook. So I'll go ahead and start up IPython notebook again, and what we'll do is we'll just start editing this third problem. So we've already done the first two, and then we're going to go on to the third one and just start with that one. Okay, so here's the work that we did on problems 1 and 2. So let's just talk about this one first. We're going to compute the adiabatic flame temperature for a stoichiometric methane air flame. And the code is given below. For much of it, we're going to add just a little bit. There's also a thermal class. So that is a class that we created from the last homework. And then we'll also need the thermodata.yaml file again. That's just a data file that contains some of the heat capacities and enthalpy functions that we're going to need for this problem. Okay, so we just have to fill in the blanks. Here we're going to, let's skip down or skip back up. Okay, so the function is the flame, this function of the flame temperature, and the temperature here is A. We want that to equal 0. That is, we want the enthalpy of our reactants and the enthalpy of our products, the difference between those to be 0. Okay, so TA is unknown. That's what we're going to be solving for, and the reactant temperature is 300 Kelvin. And we have this function here. The enthalpy of the reactants are the mole fractions times the enthalpies. At the reactant temperature, we can just compute that because we already know the mole fractions and the reactant temperature. But we're going to try to solve for the adiabatic flame temperature, the TA value. And then we have, we know that our mole fractions are, now actually I guess these have got to be mole fractions here. The MI, that would be a mass fraction though. Okay, so MI divided by MT, the mass total. And then the mass is equal to the moles times the molecular weight. Okay, and then Ni and Mi are given, and then the summation of the total mass is given right here. Okay, so let's just get, you can go through these details. It kind of talks about how to compute an adiabatic flame temperature, which isn't necessarily the focus of this class, although we do want to give these Python optimization or equation solving problems in the context of chemical engineering. So you can go ahead and read through that if you want a little bit more background on the adiabatic flame temperature. But let's just jump down here. I just want to walk through some of this code. This was from the prior homework where you defined an initialize function. In this case, we're doing one more thing, which is putting in the molecular weight. But here's our species that we're going to define, and then this initialization function, and this has 2 underscores right here. Don't forget this one has 2 on the front and on the back. Okay, and we're going to be defining the universal gas constant, the molecular weight, and then here's where we load in the YAML file, so that needs to be in your directory as well. And then we're just going to define for different temperature ranges these A low and A high. Okay, so A low, that's for the heat capacity and enthalpy between 300 and 1,000, and then a high is between 1,000 and 3,000. Here is the this is the units. This is enthalpy in units of joules per kilomole. Okay, and so there are your A values, and there is your correlation. So this function returns the enthalpy, and then here's the enthalpy in terms of the mass. Okay, so joules per kilogram. So we just divide by the molecular weight. Okay, so here is the definition of this function of the flame temperature. Okay, so we want this to equal 0 because we're comparing the reactants and the products. And so we just have the number of moles here in this is the number of moles that are defined in the reactants and then in the final as well. We also have the molecular weights of all our different species, and then we compute the mass just by multiplying the moles times the molecular weight. Okay, so this is pretty standard stuff. Now this is where it kind of gets interesting. We take that thermal class and then have our species, O2, and then also the molecular weight. So let's just go back up to that class again. So here we had the molecular weight and the species. We just leave off the self from when we call it, because that is going to be, it automatically populates that. It's kind of like a hidden argument, but it is the it's essentially the object itself. It tells you which instance of this class is calling that function later. Okay, so when it calls this one, it has to know if it's the the O2, the N2, which instance of this class it's calling, so it knows how to load in the A low and A high, and then the universal gas constant, for example, which are the self dot and then that variable. Okay, so we have all of these thermo objects right here, these instances. Okay, now we want to go down to the reactants and go ahead and under this to do, we're going to go ahead and compute the total mass and then the mass fractions. Okay, so the total mass is just going to be the summation just for the reactants. Okay, so it's going to be the mass of the O2, so that's one of our reactants right there. So mass of the O2 plus the mass of the CH4 plus the mass of the N2. Okay, so that was the reaction. Let's just go back up to the description here. So here we had just these three CH4, O2, and N2. Okay, and then our products are going to be CO2, H2O, and then the N2 again. Okay, so the N2 does not react; it's inert. Okay, so we have the total mass there of the reactants, and then let's go ahead and get the mass fractions as well. Okay, so right here, the Y. Okay, what we're going to do is do okay. See if I can reset my keyboard here. Okay, it looks like for whatever reason, my keyboard is not letting me type letters. Okay. Okay, I do not know why. I'm going to come back up here and just do a copy paste here, and maybe, oh, there it goes. Okay, so I have O2, and that's going to be the mass of O2 divided by the total mass. Okay, so that's going to be my first mass fraction, and then I have my CH4 is going to be the mass of CH4 divided by the total mass, and then N2 is going to be the mass of N2 divided by the total mass. Okay, so let's come down here to the products now. Actually, right here's another to do. We have to set the reactant temperature, then compute the reactant enthalpy. So the temperature of the reactants is going to be 300 degrees, and then the enthalpy, okay, the enthalpy of the reactants, then it's just going to be the mass fraction times the enthalpy in per mass. Okay, so we're going to have YO2 times TO2, and then we'll do dot H mass at the reactant temperature. Okay, so if we scroll up just a little bit here, we're using this H mass right here, so it's going to return joules per kilogram, and then we're going to multiply it by the mass fraction of that species. Okay, so I'm going to come down here and just complete this and do plus, and if I want to do a continuation character, like let's say the line is just a little bit too long, I can split these up into multiple lines here, and you know, the character for doing that is going to be this this backslash. Okay, so sometimes it's a little bit easier to read if I just put that backslash in there and then just do the next one. Okay, so I'm going to be summing all of these up, and this is just going to be y CH4 times T CH4 dot H mass TR. Okay, and then add in the final one, which is going to be y and then N2 times T N2 H mass TR. Okay, which is the reactant temperature. If I just line these up, it's just again a little bit easier to read. Okay, so I'm going to add up all of those, you know, the mass fractions times the enthalpy, the specific enthalpy with respect to mass. Okay, so let's go down to the next one. The next one is we want to start taking a look at our products. So we did all the calculations for our reactants. So we want the enthalpy of the reactants equal to the enthalpy of the products. So HR is going to be equal to HP, or the enthalpy of the products, but let's go ahead and compute that. So we need to first of all set the product enthalpy equal to the reactant enthalpy. Okay, so that's going to be HP equals HR. So we just defined a new enthalpy of our product. Okay, and then the next thing that we want to do is just go ahead and set the product mass fractions. It's kind of like we did for the reactant mass fractions. So I'm only going to have one that's going to be different. Let's go ahead and do that right here. Set the product mass fractions. Okay, and then instead of O2, I'm going to have CO2. Okay, and instead of CH4, I'll have H2O and H2O. Okay, so CO2, H2O, and then the N2 is going to be there as well. And then the last thing that we want to do is compute the enthalpy of the products corresponding to the current temperature of the products, then return the function. So chances are our first guess is not going to be equal to 0, but we want to use the solver to find this. So we're going to set this, we're going to return the value of HP minus, and then we want to calculate what the enthalpy is of our products. Okay, so the other way I can do this is instead of setting the enthalpy equals to HR, HP equals HR, I can just do return HP minus HR right here, and then let's go ahead and just compute HP down here. Okay, so I'm going to go ahead and compute HP, and then that's going to be Y. Again, let me just grab what I had done before. Okay, just change a couple of these characters, so I'm going to type it all out again. And instead of O2, I'm going to have CO2 and H2O. Okay, H2O and CO2. Okay, so there are my products right there, and times the enthalpy with respect to mass, the specific enthalpy. Okay, and then I'm just going to return the difference between my product enthalpy and my reactant enthalpy. And so if I have the right temperature, then I'm going to have the right, those two are going to be equal. Okay, so what I'm going to do now is let's go ahead and just set a guess temperature and then solve for the product temperature. Okay, so first of all, let's just make sure we're working correctly here. I'm just going to guess 1,000 degrees Kelvin. Okay, so I've got an air. Let's see, I've got a I've got an air here, the thermal object. Oh, you know what? I haven't run these other ones yet. Okay, so if you get that error, it means you haven't run this first block. Okay, so let me run that one, and then I'm going to come down here and run the this block. Okay, and then let's see if I get a different error now. Okay, I got the same. Okay, I got it correct. So the difference between those two at a temperature of 1,000 is quite big. Okay, let me go 11 instead, and then I can try 12, and I can keep guessing values until it gets closer to the solution. Okay, so I can keep changing those until it arrives at the correct value. Actually, you know what? The one thing I'm seeing here is I forgot to change this to TA. Okay, so let me put that as TA, and then try it again. Okay, now they're changing like I expected. Okay, so what we can do is just guess some temperatures, for example. Before we do the F-solve, I'm just going to guess some temperatures. I will do NumPy linspace. Okay, if you haven't done so already, just import NumPy as NP, and I'll just guess values between, let's say 800 and let's say 2500. Okay, and then what we can do is just print tflame as at all, or fflame at all of these different temperatures. Okay, there's going to be 50 different temperatures. Okay, let's see. It looks like it doesn't like passing in an array for this. Okay, let's see the error. Yeah, it doesn't. Ooh, okay, so it doesn't look like it likes an array for this one. So what we can do is just plug in different temperature values, 800 for example, and then 900, and just start looking at how this is changing, and then see when this is going to go to a value of 0. The other thing that we can do is just use the fsolve function, and so if we have a guess value of, let's say, 1,000, and then we can get our adiabatic flame temperature just with fsolve, and I'm going to plug in the fflame function here, and then I'll have my guess temperature. Okay, and then it's going to work on it, and if you don't have it sufficiently close, sometimes it will not give a solution. Okay, but it looks like this one did. TA, and if I guess again, okay, so 1,000 is quite far away from the solution. It's going to be probably much higher. Okay, so it's working on it, and it came up with 2,326.9. Okay, so that is in Kelvin, and let's just go ahead and check that fsolve was going to equal, give us the 0 value for fflame. So when that happens, then HP equals HR, or the enthalpy of our products equals the enthalpy of the reactants. Okay, so let's just test that solution out. And every time I click enter, it has to go in and it's doing a whole bunch of different guess values, and then computing the solution. Okay, so fflame HP minus HR is going to be equal to -3 times 10 to the minus 10th, which is very close to 0. Okay, so that concludes problem number 3, and it's kind of a long problem here, but I'd say don't get too lost in the details. This is good practice for you if you haven't seen the adiabatic flame temperatures before, but don't get too hung up on the details. Really, it's just a problem of solving a function of one variable, and essentially one big long equation, but stored in a class, and with different instances of the thermodynamics for each of those species, and then we compute the flame temperature.